So the main ones we've said we've done over here on this side, which is based on time. And the block diagram that we have corresponding to it has been this one, where we've got our output signal right there, y of t, input signal x of t, we're calling our system g. And mostly we've dealt with this one right here of working with differential equations to find our output. So for example, if we want to find that ZSR, and again, you don't have to copy it down all over again, but right here for this one, for example, that ZSR, it would be that y of t equals x of t convolution h of t. And so that was one particular way we could find the output of a system. Now we're going to turn our attention to this stuff on the right, which is frequency domain, which is a whole other way of looking at signals and systems. And at first it might seem a little bit confusing. I mean, because just about everything expressing, if you look at a signal like this, x of t or whatever, our most natural way to express a system is to just look at a plot and see how something evolves through time. So to look at like why do it in some completely different way might be a little confusing at first. But what you're going to see is that there's a whole set of advantages to working right here in the frequency domain. All right, so I got a comment in the chat if someone got kicked out. So there we go. Alrighty, so we want to switch over to this domain right here, frequency, and it's going to have a number of advantages. So as we can see in frequency domain, we can represent systems in a couple of different ways. This is the main one we're going to look at in this class, which is transfer function. Frequency response, we're going to cover a little bit more in the next course, which is controls. But the transfer function is going to be our main one. And I don't know why I keep going to this sort of diagonal setup on my camera there. There we go. So we're gonna turn our attention to that. And just I'm gonna take off my sweater. For some reason, like it was pretty chilly out there, and once you're in here, it gets pretty steamy. So if you'll excuse me for a second. Okay. Alrighty, now I feel ready after taking off the sweater, rolling up the sleeves. I feel like now I'm finally just warming up to get into some frequency domain stuff. So hopefully you're as well after that little warm up. So let's explore like why even consider, why do we even care about this? Why explore this frequency domain? Why explore the frequency domain? So again, it might seem a little bit abstract. Yes, got it. Yep, should be. Yep. So why explore the frequency domain? So we said, again, this is kind of a slightly different way of looking at signals and systems. But I'll say there are some signals and systems let's say that are more natural in the frequency domain that you can think of, I'll say that are more natural. That are more natural in frequency. Let's say in terms of frequency. So some examples of this would be anything related to sound, music, anything that involves pitch in some way. So we've like if you're looking at, yeah, like sound waves, it's going to be much easier to consider them all based on pitch than necessarily how the signals are evolving in the air, or like how, like what type of variations you have. So usually when you're talking about music, for example, you're talking about notes. And you're talking about no, that's an A or a B or a C or whatever. Then that's going to be actually all based on frequency rather than, I mean, you could look at it from how it evolves through time, but it's going to be much harder. So all this stuff, or pitch, if you talk about, for example, a higher pitch is going to correspond to a higher frequency. And similarly, lower pitch corresponds to a lower frequency. So there's going to be a direct correspondence between pitch and frequency. And so if you're looking at things from the point of view of analyzing audio, then using stuff based on frequency makes sense. And we've already done this. So one example is if you have, when we've used audio equalizer, we looked at something, for example, a bass filter. So our bass filter would take a certain signal, let's say X of t, that was just, some unprocessed audio right here. Unprocessed audio. And it would give me a certain Y of t. That was going to be, let's say, like low pitch sounds only. Okay. So if we're doing that, even though I'm writing X of t and Y of t, understanding this as the filter, basically, what it's doing is it selects signals based on their frequency, right? Like it's not going to be based on what's going on so much in terms of time, but it's going to be based on frequency. So for all these applications involving, just sound, music, pitch, all that stuff, it just makes a lot of sense. It's going to be much more natural to think about it from the point of view of frequency than it is from the point of view of how a signal looks in time. So that's one. And I'm looking at Tim McCorkle there, and I know like he's a musician, so surely that comes up a good amount, right? Like when you're looking at anything that you're doing with both music or even working with the instrument itself, there's going to be a lot of this stuff right here. I'm working with whether it's filters, whether it's looking from the sound wave from the point of view of frequency, etc. So that's going to be one. Another application where it just makes a lot more sense, I'll say another example is going to be radio. I'll say TV and other telecommunication systems. Okay, radio, TV, and other communication systems. So as an example, if you guys are listening to E-Town's college radio, you got like WWEC. That's going to be, it's going to tell you, well, that's 88.3 megahertz. 88.3 megahertz. So that means that if you're tuning to the station, there's something in there where you're looking for signals of this very specific frequency or around this very specific frequency and not others. So when we're working with radio and the type of systems that are involved there, it's all going to be based on frequency rather than on time. We're not really saying anything about what a signal looks like in time, but we are pointing out, well, these frequencies is what we're looking for. So for these types of things, like working directly in the frequency domain makes a lot of sense. Now, you might say, well, that's some applications. They're not that many. But I would say even for, so this is one of the reasons. So some signals are more natural in the frequency domain. but I'll say, but all, or even, but even for other applications. Even for other applications. So even if it's not really sound based or not really having to do with these telecommunications, I'll just say the math gets much easier. The math and analysis, let's say, becomes much easier. Now, that might be, I mean, maybe not everybody agrees. Maybe some people are like, you know what, those convolution integrals were really easy to do. That was a piece of cake. I don't really want to mess with frequency domain at all, in which case, you know, that's fine. But for most people, I would say it just becomes much easier to analyze once we are working with frequency than if we're working with time. So the reason this is the case, it boils down to this. So if again, if you've got system, let's call it H for now, and you've got this X of t and Y of t, we know, sticking just to ZSR, but we know that Y of t equals X convolution H. And we know that that convolution process can be a little bit tricky. If you happen to get a couple of signals that are both on your tables, well, you can use your tables. But if you've got something that's not on the tables necessarily, that's going to be quite messy, because you got the messy integral to deal with. Now, if you happen to have something like this, let's say a couple of systems, H1, H2, like this, and then you've got, let's call it X right here, and then Y right here. So we've got X as our input, and then we simply have just two basic systems connected, one right after the other, nothing fancy. Well, right off the bat, my Y of t is going to be X convolution H1. And this thing convolution H2. And you might guess that if we add a third one, we're going to have to convolve again. So basically for any system that involves a bunch of different subsystems, and that's going to be a lot of them, the math gets very messy very fast if you're dealing with time. With frequency, it's going to be so much better. So I think there's a lot of you that have thought, man, if it were multiplications instead of convolutions, that would be so much nicer. So that's the beautiful thing in the frequency domain. So I'll right here. So in the frequency domain, I'll have the same situation right here. So let's call it system H. But now instead of having, normally we'd have X of t, let's call it big X. And then instead of having t as my variable, I'm going to have S as my variable. Okay. This S is going to be complex frequency. Complex frequency. So all it means, it's kind of like your F and your omega that you've used in other times, but we have both a real and imaginary part to it. So we're going to use S as our frequency. And instead of having little h of t here, we're going to have big H again of S. And instead of having my Y of t, I'm going to have everything in frequency and call it Y of S. Okay. So S being my complex frequency right there. The really beautiful thing again is that if I work with frequency as my variable, everything does indeed become a multiplication. So y of s is going to be simply h of s times x of s. Which is, again, this is pretty good in most respects, but it'll be especially good when we've got those more complicated block diagrams with a lot of different subsystems all involved with each other, because that way if I combine a couple of them, I just multiply again, and multiplication is so much easier than convolution. I think everybody can agree on that. So the math becomes so much easier this way. I mentioned how a transfer function was going to be a way to represent a system. So this h of s right here, notice h of s, then it's just going to be y over x. And this h of s is, actually that's the equation that, this is what I call my transfer function. Okay. So it's going to be y over x. There's one other thing just to add here to your transfer function. This is going to be equivalent to that ZSR in a way. So this is going to be true for initial conditions equals 0. Initial conditions equals 0. So we set initial conditions equals 0, and then we do this y over x. Okay. So this is going to be, again, it's going to simplify our lives so much. And then now we've got this nice and easy and very intuitive way to represent a system. Basically, it's going to be a ratio. You can think of it as basically it's a ratio of output over input. So I'll say output in frequency domain over input in frequency domain. So it's this very intuitive output over input way of representing a system. And actually this HFS, by analyzing it, we're going to be able to figure out things like, again, interconnecting a bunch of different systems. We're going to be able to figure out things like stability, performance of our system. So all these different things based off of this description. So I'm a big fan of transfer functions. It makes everything so much easier. Again, even if your original system was not necessarily like based on sound or audio, it could be like a electromechanical system or whatever. And still, this is going to give you big advantages. So let me ask you, any questions so far? Feel free to chime in via chat if there's anything that's a little bit confusing so far. Okay, so looks like you guys are getting it so far. So you might say, wait a minute now, but how do I, that's nice and all, but okay, so we got this ratio, but I still like to think of things in time. Like I'm used to seeing a signal as evolving in time. I look at X as it evolves versus T, Y as it evolves versus T. So what's this S thing right here? So I'll tell you, like our general approach, and this is going to be true for this chapter. It's going to be true for really for the next 3 chapters. So our general approach is going to be to take a signal X of T. Again, that could be your original, whether it's a sound wave, whether it's, video, whatever it might be, your input signal. And we're going to take that and bring it over. So this is right here in the time domain. So we're going to turn this X of T from the time domain to X in the frequency domain. And we said there we can use S as our big X of S. is what we're going to have after our first step. Okay. Then we're going to run that through our system. So system. Let's call it big H of S with its transfer function. Off of that, I can find my y of s simply by saying, well, y of s again is simply the multiplication, h times x. Okay, so this is still going to be in the frequency domain. So basically everything that has to do with the system, all the processing and stuff, we're analyzing that in the frequency domain. Here, like anything that's combining a bunch of blocks together and things like that, we're doing all of that in frequency. We're finding our output in frequency, and then eventually we're bringing it back. So eventually we're bringing it back to find my y of t, which is going to be in the time domain. So again, there's basically this three-step process. You take your input signal right there, which is in the time domain. You somehow bring it over to frequency. So you're basically, you can think of it as transforming it into frequency. You do all your processing right here in this frequency domain, and then you bring it back. So in terms of how we do this, of how we go from this step to this one, how you take something in time, a signal that's, you're used to seeing it evolving in time, and put it in terms of S. So there's a couple of techniques that we can use right here. So the main ones are Laplace transform and Fourier transform. So those are going to be the two main ones. And by the way, so I'm going to use S for Laplace, but I can also have, so you can also have X of F or X of omega. And Fourier usually uses this X of S or X of F or omega. Laplace usually uses this X of S. But these are all going to be things that are in the frequency world. And then over here on the other side of things, you're going to bring it back by doing an inverse transform. So it's going to be inverse Laplace or inverse Fourier. Okay. And so Laplace and Fourier are things that you may have seen in differential equations. Again, here they're going to be just really useful tools for us so that we can get into this world, so we can get into this frequency domain realm. And right there in that frequency realm, we're going to do all our combining of blocks. We're going to do all our analysis of our system, and then we can just bring it back to time domain at the end. So this right here, so for example, if we're using Laplace, you can think of it as this fancy L signal, or rather L symbol right there. So this represents right here using Laplace. And again, I'll explain to you what Laplace is all about. Even if you haven't taken diffie-q, we'll go all into it. So you take your signal, you run it through this fancy L way of transforming it into this X of S, which is going to be with frequency as its variable, run it through my system, get a Y with a frequency, and then bring it back with an inverse. So I'll do fancy L right there. And that's going to give me my y of t, which is going to be a nice and easy signal to interpret in the time domain. All right, so this is a nice approach. Again, it kind of balances the fact that x of t, y of t are usually given to us in time. They're easier to understand in time, but all the processing is going to be easier in frequency. And so just this nice little approach here is going to be pretty useful for us. All right. So far, so good, folks. Good. All right. So, all right, I keep going into how nice and easy it is to combine things in the frequency domain. So let's explore that. Let's explore what happens when we have systems with interconnected subsystems. So let's go back to those block diagrams that we understand to a certain extent, but they're going to be especially relevant for us now. So block diagrams, let's say for interconnected systems. So now that we know about the frequency domain, this is going to be much more useful. So let's try this out. Let's say we've got a signal x of t in time, and we know that it corresponds to x of s in frequency. And let's say it first goes through h1 of s, and then it goes through h2 of s like this. And then we get y of t as our output of that. And that corresponds to a certain y of s. Okay, so I drew a big old dashed line around my system consisting of two different ones. So notice it goes through this one, then it goes through this one. And let's call this overall system, let's call it big G of s. And what I would like you to do is to express G of s, the overall system, in terms of H1 and H2. So basically, we want to combine those two blocks into one. So try that out. Here's a suggestion, a little hint. Let's consider this intermediate signal right here. Let's call that a one, let's call it big Z of S. So I'll say hint. Let's consider what happens with that Z of S, that intermediate signal. Okay, so I'll give you a minute or so to express G of S in terms of H1 and H2. Okay, and if you're over here, check with a buddy and see if you've got your same answer, or if you're working towards the same thing. If you're at home, you can like chat to a friend and just say, hey, how are you getting started with this? Are we getting the same thing or not? Okay. So do we have some suggestions over here as to what you got for your GFS? So my juniors here are pretty quiet. So how about via the chat? Do we have any suggestions via the chat as to what you expect the GFS to be? Let's we'll just go over it together. Okay, so no suggestions via the chat, which saddens me deeply. Man, I am rough start to the week, but hopefully, yeah, hopefully once you see how this one goes, you'll get more confidence as to how to simplify block diagrams. But basically, I said consider ZFS right there. So ZFS is the output of the first block. So I can say, well, based on what I know, it's just going to be H1 times X. Okay, H1 times X. Then my Y of YFS right there is going to be equal to what? It's going to be equal to H2 times its input signal, which is the input signal is going to be Z of S. Right, so then I can plug in what Z of S is. So plugging in the first equation into the second one, I get that Y of S is equal to H2 of S times H1X. Okay. And notice that I can divide right here and do Y over X, which is ultimately what I want. It's just going to be H2 times H1. Okay, because that's what ultimately that's what we want here is GFS right here. GFS is nothing other than the ratio of the output over the input. So GFS is Y over X. So this Y over X right here, that's my GFS. Okay, so nothing super fancy there, but this showed us that we can combine two blocks that are one right after the other simply by multiplying one by the next one. All right, so pretty straightforward little analysis there. Let's do another example. Let's say we've got a system right here. And actually, we've got this type of situation where we got a signal that splits off into two paths. And let's say I've got H1 up here, H1 of S. Now H2 of S down there. And then they recombine via an addition block. Sorry about that. So here they split. Then I've got my input. I'll just write it in terms of X, or S right there, X of S. and then y of s here at my output. Okay. So again, it was right there, it's split up. And then I recombined here in some, essentially think of this as an adder. Like you had a split in terms of the paths, each one got processed, it recombined, and then you got your output. So let's try to do the same thing. So let's find that overall G of S. Let's say in terms of H1 and H2. And again, recall your G of S is just going to be that ratio of output over input, Y over X. Now I'll give you a similar hint this time, just as we consider that intermediate signal before. I'll say, let's consider this signal right there and this one right here. That might be helpful. Let's call them, I'll call them Z1 and Z2. So hint, consider Z1 and Z2. Okay, so I'll give you a minute or so to try that out. All right, so John, even without me prompting, boldly tells me that Y of S is H1 plus H2. Great, yeah, I like that a lot. So I completely agree. If you got H1 plus H2, that is going to be correct. The way that that I would recommend doing this is essentially, well, let's work backward through this. So let's say that my Y of S, which is right here. So Y of S is going to be equal to, if I look up here, so notice it's going to be Z1 plus Z2. Z1 plus Z2. But in turn, my Z1 is going to be H1 times X. So notice the X is here and the X is right there. So Y of S is going to be equal to Z1 times X of S. And then similarly, Z2 is going to be H2. Oops, my apologies there. This is going to be H1 times X. And similarly here, so this is my Z1. And my Z2 is going to be H2 times X. Okay, and then of course I can factor out X. So I get H1 plus H2. And finally I can divide, right? So I get my Y of S over x of s is equal to just that h1, to be as thorough as possible, h1 of s plus h2 of s. And this is equal to what I was looking for, the g of s. So indeed, there we've got a nice description of my overall system. So for this configuration, again, it's going to be a simple addition. If I have a couple of them in a row, it's going to be a multiplication. So that's, and again, we analyzed it. Again, notice when you've got a more complicated one, you can always go into those intermediate signals and just, express each multiplication as needed. Again, if we were working back with time, even this thing would be a convolution, H convolution H1, H2 convolution X right here. So it would already be pretty messy, even with such a simple system as this one. So we were already figuring out, okay, this is how we would combine those. Let's do another one, combining some of those concepts. So let's do one that we've worked with in the past, which is our good old audio equalizer. So audio equalizer, and I'll say, let's find that overall transfer function. Okay, and let's do it right here. So we've got a signal X coming in from the left. Let's call it X of S, and it splits up into 3 paths. So here we have a base filter. Here we have a medium filter. And here we have a treble filter. So each of those is going to have their equations with S as its variable. So let's call them H1, H2, H3. H1S, H2S, H3S. And then we would have an adjustable amplifier corresponding to each of them. So an adjustable amplifier. So an adjustable gain for each of the 3. And let's call these K1, K2, and K3. So again, those would be amplifiers that you can either dial up or dial down, depending on your audio preferences. And then eventually each of these 3, we're gonna bring over to an adder circuit. Just add them all together, and that gives me my output, big Y of S. Okay. So this whole thing and yeah, so these are all going in here with a plus sign. So this whole thing is going to be my audio equalizer, and again, let's call it big G of S. So let's find that overall transfer function G of S in terms of K1, H1, and all that. All right, so try that out. And again, when in doubt, I encourage you to consider sort of these intermediate signals right here. That might be helpful. All right, so if you're here in the class, check with a friend. Otherwise, yeah, if you're at home, you can type to a friend to double check.
You did the H2 again, so did you do X times H2 again?
Okay. Okay. All right, folks, so let's go over it together. So over here, I put my intermediate signals. I call them Z1, Z2, Z3. So for example, my Z1, which is up top, notice I actually have X in each of those places. So we know that we can combine these two into one block. So it's going to be K1, H1X. Z2 is going to be K2, H2X. And Z3 is going to be K3, H3X. Again, by using what we already know from how to combine blocks where they're in cascade, one right after the other. So we can use that. And then for my adder, I know that Y is going to be equal to Z1 plus Z2 plus Z3. Therefore, I can say that Y is equal to, I can plug each thing in there, K1, H1X plus K2, H2X plus K3, H3X. I can then factor out X on the right and say, well, and I'll bring it down here. So Y over X is going to be K1, H1 plus K2, H2 plus K3, H3. And there we go. And so that would be our overall transfer function there for our system. This is overall transfer function. Great. All right, and so notice that already this was a system that was already quite a bit more complicated than the ones that we've seen so far. And every single multiplication that we see would have been a convolution if we were working in time. So right off the bat, we're like, okay, even with a system like this one, this is going to be much easier by sticking to these frequency techniques. Let's do another example. All right. So let's go over here. And this one might be, I don't know, maybe you'll find it super easy, maybe not. I think it's deceiving because we're only just going to have two blocks. So we're going to have X right here. Then we're going to have a little summation point here. This is going to go through system, let's call it right here, H1. But then this thing is going to do this. It's going to split and come back this way through H2. Okay. And H2 is going to go right there. Let's say furthermore that this X is going right here with a positive sign. This is going right there with a negative sign. So this thing is subtracting off when it goes into that little adder circuit. And then on my right, I've got my Y. Okay, so I got X of S, Y of S. So it's kind of this little feedback style configuration right there where we kind of go through and go back. So try that one out. Let's find the overall transfer function of the system. Well, let's use a different letter. Let's call it big T of S, which is Y over X. All right, so So try that one out. Again, notice those intermediate signals might be a good way to try it. So notice we've got one right here and we've got one right here. So those two might be useful. Okay, so I gave you the hint of considering these two. I'll call this one right here E of S, big E of S. I'll call this one right here M of S, big M of S. Okay. All right. So if someone already has an answer, feel free to let me know, raise your hand and tell me, or type it into the chat. Again, this one is surprisingly tricky. I think for just having two blocks, it's a little bit more involved. Okay, so otherwise, no worries. Let's go over this together. Notice that over here, my Y of S, so this right here that's coming out right here, this is already Y of S. And Y of S is splitting back in here, so this is also Y. But my Y is coming straight through, and so I can say that Y is equal to H1 times E, right? Do you guys agree with that? Right off of that, like if I look at this, Y is equal to H1 times E. And if at some point you're like, I don't buy that, let me know. Now, E in turn comes out of the summer. I'll say E is going to be what comes out of here, and it's going to be X minus M, right? Notice X goes in with a positive sign, M goes in with a negative sign right there. So E is X minus M. And so I can, eventually what I want is Y and X. So you know what, I'm gonna plug this in here and start, so if I plug that, the second equation into the first one, I'm gonna get that Y is equal to H1 times X minus M. Okay, just because I want Y and X there in one equation. So I'm plugging in the E. Okay. Now I'm already in pretty good shape and I got Y and X. However, M is still a problem. So I would write M as whatever it is. Notice M is coming over here leftward. So M is coming out of this one. So M is going to be H2 times Y, right? Let's say, but M in turn is H2 times Y. Do you guys agree with that? You see, so this is a little bit, it's perhaps a little confusing in that it's going in the other direction. The input is coming in from the right side, the output's spitting out here on the left, but this output M is going to be H2 times Y. And so we can plug that in and say, well, so this I can plug into there. So therefore I can say Y is going to be H1 times X minus, and then instead of M, I write H2Y. Okay. And so now this is good because I've got an equation that just deals with Y and X. So I can simply factor things out, move them around. So notice I would have Y is equal to, I'll multiply through here, H1X minus H1, H2Y. I'm going to bring all the Y terms over to the left side. So I'm going to get Y and then 1 plus H1, H2 equals H1X. So basically I took this term over to the left and factored that out. And so now I can do my ratio and say, well, Y over X is going to be H1 over 1 plus H1, H2. All right. And so that right there is going to be my overall transfer function. And it turns out that the little feedback configuration is actually super useful. And especially next semester when we go into control systems, we're going to be doing feedback loops all the time. And so getting comfortable with this feedback loop right there when, yeah, just kind of being used to this particular structure it's really going to help us out. So question with this one right here. All right. So let's do, I can give you a couple of tougher ones and assign them as homework if y'all want. Get into a rhythm. Why not? So let's try this out. Let's do this example. Or I mean, yeah, no, let's do that. I was also thinking we could showcase just like we did for the equalizer. Actually, you know what? Let's do a cruise control example, just so you guys get more examples here with practical systems. So cruise control system. So notice a cruise control system. You can look at it in different ways, but I'll draw it this way. So let's say that I've got let's say the car's body. We can think of that as a system. And right there, its output is going to be, like the output that I want is going to be the speed of the car. Okay. So the speed of the car is going to be my y of t. Then over here on the far left of the page, I'm going to have what would be the input of my cruise control system, which is the desired speed. Desired or reference speed. So I put desired speed right here. That's my x of t. All right. So desired speed is my x of t. My actual speed, so the speed of car, is going to be my y. Now, in order for my cruise control to work, I would take this actual speed and I would run that through a sensor. So let's say, you know, a speedometer. Yeah, let's say speed sensor right here. And notice right here, this signal is going to be my measured speed. And then usually that's going to do is I'm going to compare my desired speed to my measured one. So I'll bring this up here, compare the two. Okay. So this is going to be a comparison. Say comparison point. So my comparison point is going to take my desired speed compared to my measured speed. Usually the way we compare, there's multiple ways to do it, but the easiest way is to subtract the two. So if I do desired speed minus measured speed, then it's going to give me the difference between the two. And it's going to tell me if I have a positive number or I have a negative number, it's going to tell me, am I above, am I below? Do I need to speed up, slow down, that type of thing. So we're going to have a comparison point. This usually goes to a computerized controller that based off of the decision gives an instruction to the car. So I'll say here it goes to, let's say computer. And this computer it's just going to decide, depending on how big the signal is, whether it's big, small, positive, negative, it's going to decide what to do, whether the car needs to slow down or speed up. Then that's going to send a signal to my engine. And that in turn, the engine is going to make the car's body move. So you end up with this type of situation. Okay, so it's a pretty typical breakdown of how the signal flow would work in a cruise control system. So let's find that overall transfer function. Let's find the overall transfer function. Let's call it TS of cruise control system. Okay. And just so we have all the same letters, so I call this X of t on the far left, I call this Y of t on the far right. And these systems, I'm going to call the computer K. I'm going to call my engine G1. I'm going to call my car's body G2. And I'm going to call my speed sensor H. And that's all of them are S. Okay, folks. Now, this is one that if you do it step by step, or if you do it from scratch, it might take you a little bit longer. Or it could take you no time at all if you observe certain patterns about it. So if you kind of observe the structure and think about the examples that we did in this class earlier and kind of integrate those examples, you might be able to figure out pretty quick. You might be able to figure it out pretty quick. I will give you the hint if you want to do it perhaps more, get more practice, do it little by little or do it from scratch. As usual, let's consider those intermediate signals. So this signal right here, let's call it E of S. And this signal right here, let's call it M of S. So if you write the equations for those, it might help you out. But again, if you're pretty clever about it, you might not even have to. So folks, it's 10:41, so I'll leave you in suspense with this one. I'll say try to finish it up on your own, but we're going to start Thursday's class by going over this example together. Also, I'll assign a homework either tomorrow or Thursday, or I'll have you simplify some of these more involved block diagrams like this one. Again, notice that this is, a practical system with a bunch of different components that we can combine, and then we can say a lot about our overall system. And then this one doesn't even have to do anything with audio and pitch and all of that. Yet these frequency techniques are going to come in handy. So yeah, so I'll send you a homework. Either I'll post it on Canvas tomorrow, or I'll shoot it to you on Thursday. But for the time being, try to do this one on your own, and we'll get started with that. Okay, folks. Other than that, we are done for today, and I'll see you on Thursday.